This is Algebra 2 with Trig, working on the Semester 2 Exam Review, Unit 7, Sequences and Series. So what we're looking for is the sum. This is an arithmetic series. So a couple different ways to do it is to plug in 1. If you plugged in 1, you get 3 plus 2, which is 5. Plug in 2, we get 6 plus 2 is 8. Plug in 3, 9 plus 2 is 11. Plug in 4, 12 plus 2 is 14. And plug in 5, 15 plus 2 is 17. You could do it like that, and then you could add them all together. That's one way to do it. That doesn't help very much if this number was much larger. It's not very realistic to add all the terms together. So we have a formula. If it's an arithmetic, series, then we're going to do the sum by doing the number of terms times the first term plus the last term divided by 2. So it's the average of the first term plus the last term divided by 2 makes it the average times the number of terms. So A of 1 is when you plug in this value into your term. We've already done that, but it would be 3 times 1 plus 2. So A of 1 is 5. And then you get your last term by plugging in the top number into your rule. So that's 3 times 5 plus 2. That's 15 plus 2 is 17. And the number of terms, as long as you're starting with 1, it's going to be this top term, top value, called the upper bound. But we have to start with 1 for that to be the case. So if it's not doing that, you just got to watch out. We're plugging in a 1, then a 2, then a 3, then a 4, then a 5. There are 5 terms. So the total sum is 5. 5 plus 17 divided by 2. That's 22 divided by 2, which is 11 times 5. Find the sum of the arithmetic series. So here we're just doing the same thing again. We're going to use the formula, term, first term plus the last term divided by 2. And we have to figure out what the first term is, so you plug in a 1. That's 2 plus 7 times 1, which is 9. The last term is going to be plugging in a 12. So that's 2 plus 84. So that's 86. Now this would be an example where figuring out every term, you have to do it 12 different times. That would be a lot of calculations, not very realistic. So that's where the formula really starts to help. And the number of terms, since we're starting with a 1, it's going to be 12. So n is going to be 12. Okay, so we have that. We can do a couple different things. We could divide the 12 by 2. We could add these two together and get 75. And divide that by 2. And 6 times 75, if it was 100, that would be 6 times 100 is 600. But then you've got to take away 6 25s. So that's going to be 450. I believe that's 450 is our sum. This is infinite. So how we know this is infinite is we're looking here at that term there. That is infinite. That means this series goes on forever. You're going to plug in a 1 for the first term, you're going to plug in a 2 and a 3 and a 4, and it goes on forever. But there is a total sum. For there to be a infinite sum, the geometric series must have a ratio greater than -1 but less than +1. The R value has to be between -1 and +1. For the geometric series to have an infinite sum, the ratio has to be between -1 and 1. Our R value is -1/2. That falls in between -1 and 1. So the infinite sum is going to be your first term divided by 1 minus R. So our first term is when we plug 1 into this. So you plug 1 in here and you get 1 minus 1, which is 0. Any value to the 0 power is 1. So A of 1 is 1. And our ratio is -1/2. So we're actually adding 1/2. So we're 1 over 3/2. And to handle that, you multiply by the reciprocal. So it's actually 2/3. 2/3 is the total sum. Questions about that? We recognize there was a little flaw up here. Somehow 86 plus 9 became 75, but it's not 75. It's 95. I guess I should just use a calculator and not try to talk and do this at the same time. That's 95. So that whole concept of dividing the 12 by 2 is just fine. So you have 6 times 95. If that was 100, that would be 600, but I'm going to do 5 less for every 6, so that's 30 less than 600. So that should actually be 570. A calculator would keep us out of trouble than mental math, but 570 it is. All right, here's another infinite geometric series. What is the sum? Is R greater than -1 and less than 1? This R value is 1 1/4. 5/4 is 1 1/4. This is bigger than 1. So this increases forever. So you cannot do a sum. No sum. The R is too big. Write an explicit rule for the nth term of the geometric series. So an explicit rule A of 1 times R n minus 1. That seems right. So now what we don't know is what is our R value. So our R value is the term divided by the one before it. So 4 over 5 should be our ratio. Let's try it again. Let's take the term divided by the one before it. Well, that doesn't look like 4/5. Well, one way you could do this is times it by 10, times it by 10, so we don't have a decimal anymore. And then we can simplify that. I see that 8 goes into this top number 4 times, and 8 goes into the bottom number 5 times, and look at that common ratio. Okay, it's 4/5. So our rule is 5 times 4/5 to the n minus 1. And we can test that. It's always good to test it. 5 times 4 divided by 5 raised to the n minus 1. Well, if this is the first term, and that's the second term, and that's the third term, and that's the fourth term, let's do 4 minus 1 and see if we get 2.56. Hey, it worked. Write an explicit rule for this geometric sequence. Well, notice how they're alternating every time. Positive, negative, positive, negative. That means we're multiplying by a negative each time. You can do the same rules that we did before. Negative 4 divided by 1, which equals negative 4. 16 divided by negative 4, which equals negative 4. Negative 64 divided by 16, which is negative 4. We get this common ratio of negative 4. So our rule is going to be the first term, which is 1. You don't really need to write that, times negative 4 to the n minus 1. And we can test that. Parenthesis, negative 4 to the 1, 2, 3, 4. Let's just do the fourth term and see if we get negative 64. There it is. Find the sum of the infinite geometric series. So what's the sum of an infinite geometric series? Is that even possible? Well, we talked about that was possible if the r value was greater than negative 1 and less than 1. So we're taking half, taking half, taking half. So r equals a half. So yes, that's going to fall into that. So S infinity equals A of 1 over 1 minus R. That's your formula. That's what you want on your note card. So 8 over 1 minus R. So that's going to be 8 over a half, which is 16. 8 divided by 2 is 4. So don't say 4. 8 divided by a half, you multiply by the reciprocal. 8 times 2 is 16. Find the sum of the infinite geometric series. So infinite geometric, it looks like we're multiplying by negative 2, then we're multiplying by negative 2, multiplying by negative 2. So the r value is negative 2. The r value is not in between that range. There is no sum. For an infinite, for it going on forever, it has to have a ratio that falls in between here. Any concerns about that? Okay, write a recursive rule for the sequence. Recursive. What I notice here is that we're timesing by 2, and we're timesing by 2, timesing by 2. So this is geometric. So a recursive rule has to have the first term. That's the most common thing that we forget. In a multiple choice format, I guess it really won't make a difference because that'll probably be included. But that's what people usually forget is their first term. So there's our first term, and then the rest of the pattern is taking 2.5 times a of n minus 1. So the rule is a of 1 and a of n is going to be no, I messed up. This is the previous term. What is my ratio? Just 2. There you go. So it's r times a of n minus 1. The 2.5 was my a of n minus 1. That is the term before the one you're looking for. So if we're looking for the second term, we have to look at the first term in this spot and times it by 2. And that's how we got 5 for our second term. Write a recursive rule for this sequence. Here we're plussing 4, actually subtracting 4, and subtracting 4, and subtracting 4. So this is arithmetic, where the common difference is negative 4. So with the recursive, you always got to start with the first term. And then our rule is going to be a of 1 plus d n minus 1. A of n equals that. So to figure out our next term, what we're going to say is our first term plus our common difference, which is a negative 4, n minus 1. Distribute that through. Negative 4 n plus 4 gives me negative 4n plus 6. And that's assuming that we start with 2. So let's test this theory. Let's see if I did this right. So we know the first rule is, or the first term is 2. And then we plug the 2 in here, and we get negative 8 plus 6, which gives me negative 2. Then we plug the negative 2 in here, and that is 16. Oh, negative 2 in here, that's 8. Maybe not. All right. I see what's wrong. This is an explicit rule. It's not going to work this way. This rule, if I want to get my fourth term, I plug a 4 in here. So negative 4 times 4 is negative 16, plus 6 is negative 10. Works out great. But we're supposed to be doing a recursive rule. My bad. Sorry about that. I did the explicit rule. So what we do here is a lot easier. It's the previous term plus our common difference. So let's test that. Let's take the 2 our common difference is 4. So we're going to take our 2 and we're going to minus 4 to it. We get negative 2. We're going to put negative 2 in there and minus 4 to it to get negative 6. Plug negative 6 in there, minus 4 is negative 10. There we go. So it's always good to check your work. I didn't do math wrong. Math was correct. It was a rule for that series, but it was the explicit rule, not the recursive rule. The recursive rule requires us to use the previous term. So this is your previous term, a of n minus 1. Here's an example of a recursive arithmetic. Recursive arithmetic. Okay, so we're supposed to figure out the fifth term. Well, the first term is clearly 1. The second term is 1 plus 3. The third term is 4 plus 3. The fourth term is 7 plus 3. And the fifth term is 10 plus 3. 13. Questions about that? Find the third term of the sequence. Well, the first term is clearly 2. The second term is 6 times the previous term, which is 12. So the third term is going to be 6 times the previous term, which is 72. Find the fourth term of the following. This is an explicit. Explicit arithmetic. So if you want the fourth term, a of 4, you just plug a 4 right into the problem. That's 28 minus 3, which is 25. Explicit is way cool. Find the 20th term. A of 20 is going to be negative 2 times 20 plus 21. Negative 40 plus 21. Looks like negative 19. What is the next term in the sequence? Well, it looks like we're adding 6, and we're adding 6, and we're adding 6, so we're going to add 6. We get 22. What's the next term in the sequence? Looks like we're cutting it in half, and cutting it in half, and cutting it in half. So we're going to take 1.5, which we can call that 3 halves if we like, and we're going to multiply that by a half. We get 3/4. So you could call that 0.75 if you're using a calculator, or just 3/4 if you're doing it without a calculator. One term of the arithmetic sequence is a of 19 equals 48. The common difference is 3. You could use y equals mx plus b, where x was 19 and y was 48, and your slope was 3, and you could solve for b and have your rule. Or, like I was trying to do earlier, we're writing an explicit arithmetic. Here's what we would do. We would put our 48 here. Our first term is what we don't know. Our common difference is 3. We get 48 when we plug in 19. So 3 times 18 is 54. We subtract that underneath, and it looks like we're going to have negative 6. So a of 1 is negative 6. So if a of 1 is negative 6, then we're ready to simplify this out. Negative 6 plus 3n minus 3, so that's 3n minus 9. And we should be able to test this out. If I plug in a 19, so 3 times 19 minus 9, I should get 48. Perfect. We have an arithmetic sequence. The 11th term is negative 57. We know our common difference is negative 7. So the formula we're going to use is right there. So you can plug in your negative 57. What we don't know is our first term. Our common difference is negative 7. So you can just put down minus 7. We get 57, or negative 57, when you plug in 11. So that's negative 57, a of 1, minus 7 times 10. So 7 times 10 is 70. We're going to add the 70 to the other side. So a of 1 is 13. That's what we're starting at. So if we start at 13, and we subtract 7, and we do it 11 different times, we should be at 57. So to figure out our rule, we plug in our first term, we plug in our difference, and we have n minus 1. Now you cannot call this 6. Do not say 13 minus 7 is 6, because it's not 7. It's 7 times something. So I'm going to distribute. And that gives me a rule of negative 7 plus 20. And we can test that theory, test that rule. We have negative 7 times my 11th term, add 20 more, that gives me negative 57. Worked out great. Is the following sequence arithmetic, geometric, or neither? So the test, the geometric test, is a term divided by the one before it. Do you have a common ratio? So here, we're going to say 16 divided by 64. 16 goes into 16 once, 16 goes into 64 4 times. That doesn't mean anything. It's just my ratio. Now I get my 4 and divide it by the one before it. And that can be reduced. And then my 1 divided by the one before it. There's my common ratio. This is geometric. Is the following sequence arithmetic, geometric, or neither? Well, if this is a geometric rule, you can take the term divided by the one before it. 4 divided by 1 is 4. 9 divided by 4 is 2 1/4. No, this isn't geometric. We're not multiplying by the same term to get to the next term. So that's not it. An arithmetic test is going to be a term minus the one before it. So 4 minus the 1 is 3. 9 minus the 4 is 5. 16 minus the 9 is 7. That's not the same number every time. It doesn't have a common difference. So nope, not arithmetic. So this falls under neither. You probably realize that this is 1 squared and 2 squared and 3 squared and 4 squared and 5 squared. So it's the position being squared. That's the actual rule. And you can see that that is not arithmetic and that is not geometric. Find the sum of the series. So we've determined that the sum, this is geometric, so that's a of 1 times 1 minus r to the nth power and 1 minus r. That should be our rule you want in your note card. To figure out our first term, we need to plug in this bottom number into our rule. So we plug it in. 1 minus 1 is 0. 4 to the 0 is the value of 1. So our first term is 3. We need our common ratio. Well, that's the value in the parentheses. That's the value that's going to repeat by multiplying. That's the 4. So the R value is 4. The number of terms. We're starting with 1 and we're going up to 4 different terms. So that's 4. That's everything we need. So the sum is going to be 3, 1 minus 4 to the 4th power over 1 minus 4. So we have 3 times. Now we have a numerator, so I'm going to put that in parentheses. 1 minus 4 to the 4th. That's our numerator. Divided by our denominator, 1 minus 4. And we close parentheses. That gives us 255. So this is easy enough. You could easily plug in a 1, and then plug in a 2, then plug in a 3, and plug in a 4, and you would eventually be able to add all those terms together, and it would be 255. You could try that. We knew this was geometric because of the way this rule was written. Geometric rule is going to be your first term times your ratio n minus 1. That's for the geo rule, geometric rule. Arithmetic rule has to follow this, and we typically can reduce it so it looks like y equals mx plus b. It would probably be like 3n minus 2 is what it would reduce into, depending on what the numbers were. Okay, find the sum of the series. I see this, and again, this is geometric. This is a finite geometric. Finite geometric, we could plug a 1 in, then a 2, and a 3, and a 4, and a 5, and we could add those 5 terms together, and we'd have our sum. Or we can use the rule. It would be S of n, because it's a sum. Is the first term, 1 minus r to the nth power, 1 minus r. There's our rule for a finite geometric series. So we know our first term is 10. We know our ratio is 3/5. We know our number of terms is 5. We're ready to plug that into our formula. 10, 1 minus 3/5 to the 5th power over 1 minus 3/5. So we have 10 times, the numerator needs another set of parentheses around it, 1 minus, I have a fraction, so I'm going to put parentheses around that, 3 divided by 5, and that fraction is being raised to a power, and that's the conclusion of the numerator, and we divide that by 1 minus, I use another set of parentheses around the ratio, and that closes off my denominator, which closes off my entire question. Looks like I get 23.056. Sigma notation. So we got to come up with a rule for this. We know that this is, it looks like we're adding 5 and adding 5, so this is arithmetic, where my common difference is 5. I just don't know how many terms are in here. So what we can do is take our rule, plug in our 100. Our first term is 5. Our common difference is 5. I just don't know how many terms I have to get to 100. So this is 5 plus, distribute that through, 5n minus 5, so those cross off. So if we're counting by 5s, there'd be 20 terms to get up to 100. Makes sense, 20 times 5 is 100. But we verified that. So our sigma notation, if we start with 1, which I would suggest you'll always start with 1, you know that there are 20 terms to get up to 100, and now you need your rule. Well, we did the rule. Be A of n, 5 plus 5 to the n minus 1. There's the rule. And our last question, write the sigma notation. This is geometric. The common ratio, it looks like a 3's on top every time, and the 4's being multiplied on bottom. What are we going to have to do to get all the way out to here? Well, you could think about it a couple different ways. There's the rule. So if you wanted to use 3 over 4,096, and your first term was 3, and you're looking for your R value, no, we know our R value. Our value is 3/4. But you're solving for the exponent. You could use logarithms for this. Okay, so we're going to divide by 3, which is going to cross the 3's out. So that's going to give us 1 over 4,096. Okay, then you do a logarithm. Base 3/4 of 1 over 4,096 equals n minus 1. Seems a little crazy to do it like this, but it works. And we know a couple of ways we could do this. You could go to second window down to number 5. That's that change of base. And you could just plug in your 3 divided by 4 and your 1 divided by 4,096. All right. Not exactly what I was expecting. Let me just take a look. My concern is that I'm getting a decimal of the number of terms. I'm going to add 1 to it, but I'm still, that would be weird. Let's test this. Let's start with 3. Let's times this by our ratio of 3/4. I'm going to times it by 3/4. Oh, that's my issue. Ah, no. My ratio is not 3/4. My ratio is 1/4. The ratio is just 1/4. That's why this didn't work out. We multiply the 3 by 1/4, and we multiply by 4 on bottom every time. So that is what we have. So if I wanted to do it by hand, like I was showing you here, we would need to do all that craziness. And that's going to probably work out a lot better if we were to do it in this method, which was 1/4. 1 divided by 4,096. There's my 6. Add the 1. There are 7 terms. Phew. But that's kind of weird. We typically wouldn't have done it like that. I would just expect you to kind of do it like this. You'll start out with 3, and you'll times that by 1/4. And there's your second term. There's your third term. There's your fourth term. There's your fifth term. There's your sixth term. And if you ever want to figure out what that value is, you can go to fraction. And you can see that that's not quite what we had. So we're going to times that by 1/4 again. And that is the fraction that we're looking for. So there are 7 terms. And our rule is the first term times the ratio n minus 1. Finding the number of terms can be tough.